In this video, we're going to start looking at AIs that actually learn from their environment and their experiences in the environment. So in the last video, we looked at Markov decision processes, and these will be the models we use to represent the environment. And we talked about how we can reason about policies and rewards in the form of estimated future rewards in terms of the utility function. So just to look over some of the things we saw in the last slides, let's revisit the Bellman equation because it's going to come up a few times in our learning when we discuss learning algorithms. So this is the Bellman equation, and what it says is that the u function, this u of s, is the estimated future reward, discounted future reward when you start in any state if you play optimally. And sort of by a kind of a circular definition, the optimal strategy is also defined as choosing the action that gives you the highest expected future utility. And just as an aside, you might come across, and you will come across in your homework, an alternate version of the Bellman equation where we define the Markov decision process as giving you a reward not for entering a state, but for taking a certain action in a certain state. So this alternate version, shaded in gray, is slightly different, where we moved around where the reward is on the right-hand side of the equation, but it's roughly the same idea. So at this point, it's useful to think about, looking at the Bellman equation, what are the quantities that we have access to in a typical situation? So typically, we will have pretty good access to the reward value, because as we move around the environment, our agent will actually receive rewards or penalties. So the agent will be able to observe or record rewards that it receives in certain states. And then there are other terms in the equations, like this probability distribution of the transition probability, of the transitions given a state and an action, that an agent doesn't really have access to, at least in most settings. Right? An agent only gets to see what happens after it tries an action in a particular state. It doesn't really get to see what the probability of all the other possible transitions were. In addition, the agent, for the most part, will try certain actions in certain states, but it doesn't get to do a full max over all possible actions. So it can't really see the result of all actions. It can only see the result of the actions that it performed. And then lastly, we, as the agent or as the AI engineer, we don't have access to the utility function. This is something that we would like to discover. So in the last video, we talked about an algorithm that if we actually did have access to all of the transition probabilities, then we could, and the rewards, we can compute the utility value. And there are a bunch of drawbacks to that algorithm. This was the value iteration algorithm. It computes the utility for every single state, which is good, but it needs the exact transition model. It needs to fully observe the state, and it needs to know the exact reward for each state. And we'll talk about, in this video, approaches for addressing the two underlying points. And we will also discuss how to address the other two non-underlying points, either in a later video or in class. So to start the discussion about passive reinforcement learning, let's think back to the slippery bridge example. So in this picture, we see all of the reward values for all the states, but what we don't see on the screen, because it's difficult to draw, are the transition probabilities. And it's important to remember that as an agent exploring this environment, the agent doesn't have access to even the rewards that we're seeing on the screen, and it certainly doesn't have access to the transition probabilities. What it has access to instead is the direct interactions with the environment. So it can try random things. In this case, maybe it tries moving right. I'm not showing what the actions are. I'm showing the resulting transitions. But let's say it tries a bunch of actions and it ends up taking this path. Maybe it lands there at some point. It goes back and and so on. This goes on for a while. Okay, and etc. So the idea is that we are going to consider an algorithm whose input is going to be a history of what the agent tried to do, so the actions that the agent took, and the resulting transitions that occurred, and the rewards that came with those actions and transitions. And if we're able to learn a good policy or a good utility function or something about the environment, then with just that information, then what we've done is something called passive learning or passive reinforcement learning. And to contrast this with what we've done with value iteration and with what we're going to look at next, which is called active reinforcement learning, let's think about the properties of these things. So let's think about what we have access to in the different forms of the algorithms. So in value iteration, we have access to the full states and rewards and transition probabilities. Right? So we have the whole description of the Markov decision process. And the decisions row on the bottom, I'll get to that later, but for value iteration, there's no real decisions happening. There's not even an agent. We're just sort of, as an AI algorithm, we're sort of staring at the transition probabilities given to us, and we just do a bunch of computation on it, and we output some utility function. So there's no notion of a real agent in the space doing any actions or making any decisions. Now, in passive learning, we only observe the states and the rewards visited by the agent, right? So no longer do we have access to all of the states, nor to the transition probabilities. And then in terms of transitions, we observe only the transitions that occur from the chosen actions. So that's a much smaller set of information that we get than with value iteration, right? Because we only get to see, which transitions actually happened for the actions that we actually chose. And then in terms of decisions, in passive learning, the learning algorithm does not get to choose actions. We just look at a history of, an agent doing an exploration in the environment, and we didn't have any choice in what the agent tried to do. So active learning has the same type of observations for the first two rows. So the states and rewards, it gets to observe only what the agent visited. The transitions, it only gets to observe which transitions occurred given which actions that the agent actually tried. But the difference is that the active learning algorithm gets to choose the actions. So in this video, we're focusing just on passive learning, and we'll look at active learning next. So in passive learning, the analogy is that we just get a recording. We get a videotape or a log of our agent or an agent behaving in the environment and doing some actions that we don't really need to know or have access to what the reason was for all the actions that the agent chose. We just get to see which actions the agent chose and which resulting transitions occurred and the rewards that the agent got. So the three types of passive learning we'll talk about in the video are direct utility estimation, adaptive dynamic programming, and temporal difference learning. And almost at least 2 out of 3 of these don't really have any English interpretation in terms of them making sense to you by just looking at their names. The first one, maybe you can guess, direct utility estimation. Maybe you can guess what that is. But the other ones, just bear with the jargon, and I'll explain how each of them works. And just to inject a little opinion here, my favorite of these algorithms is temporal difference learning, although adaptive dynamic programming has some advantages over TD learning. And direct utility estimation, as you'll see in a couple minutes, is really just a thought experiment because nobody would ever use direct utility estimation in practice. Okay, so with that said, here's what direct utility estimation does. So it looks at the Bellman equation. This is just the old Bellman equation, and instead it's going to think about something else, a different form of utility, not the utility that is defined by the maximum policy or the maximum or the best optimal action at each state, but the utility defined by a fixed policy. So you can see the difference here is that now we've put a superscript of pi to describe that this is the utility for a particular policy, and the superscript appears here as well. And the intuition is that this is now going to define the future reward of a state, assuming that we use this policy pi. And the major difference in the equation is that we've replaced this max over all the actions with just a lookup of what the policy says the best action is. And it doesn't even say what the best action is. What the policy says its preferred action is. But again, it has the same decay discount factor concept and the expectation over what state you'll end up in given the action that is chosen by the policy. So it's very similar to the original Bellman equation, but now it's about the particular policy pi. And I will just say what direct utility estimation is in English because it's such a kind of naive idea. Is really just a thought experiment. So what the direct utility estimation does is it looks at in your log of the agent exploring the space using policy pi, we essentially have records of what the future reward this agent experiences after visiting each particular state that it did visit. So we can use each of those estimates of the future rewards from our log, discounted by gamma, and essentially run your favorite learning algorithm on this kind of data. So we basically just have, a sample for u pi of s for every single time the agent entered state s, and we just, basically we just take the average, right? We take the average value, and that's our estimate of the expected utility. So it's a pretty naive idea because basically we're just assuming that the utility of every single state is just an independent quantity that depends on the state. But we know in reality that there's a lot of dependencies here that depend on these transition probabilities. So the other learning algorithms think more about the relationship between these utility values. Direct utility estimation doesn't think that doesn't work as if there are any relationships at all, and just tries to estimate the utility of each state separately. And what you essentially need from the data collection process when the agent goes out and explores the world is that you need the agent to get lots and lots of samples of entering each particular state and moving on from there. So with that said, adaptive dynamic programming is the next version we're going to look at, the next version of passive reinforcement learning we'll look at. And in this algorithm, it's also going to do something kind of a little bit on the naive side in the sense that it's just going to try to learn certain quantities from just lots of our independent observations as our agent explores the environment. So it's going to record all of the actions that it took, and then it's going to try to estimate the transition probabilities and the rewards. And we pretty much assume that the rewards are a fixed function, so there's not much estimation to be done. It's really just, just memorize the reward when you enter each state. So the hope is that we've entered every single state. So what adaptive dynamic programming does is then it essentially will store this other data set, which is going to be, in this particular state, in each particular state, which actions have I tried and where did I end up going after I tried those actions. So in this, for the beginning of this trail that I've been showing you, the first action the agent maybe tried is to move right, and it slipped off the bridge and went up. So it records that and it remembers that there's some probability. Well, now we have some evidence that there's some probability that moving right from this space results in up. And then next time it enters this state, maybe it tries moving right again, and this time it moves to the right. So now it has some data that sometimes you do successfully move right. And then again from this state, let's say it tries to move right again, and this time it really does move right. So good, and more evidence that moving right is sometimes successful. And then again, next time it enters the state, it tries to move right again, and this time it goes down. Okay, so now we have evidence that, sometimes we slip down also, and so on. And maybe we try right again next time we enter, and we successfully move to the right. So with this data, we can now estimate the transition probability of using the right action from this start state. So the idea is then we can just estimate this transition probability. So we have an estimate of the transition probability. And from recording the reward values that we got, we have an estimate of the reward values. And once we have our estimate for the reward value function and the transition probability function, we can run value iteration and learn the utility function. And not just the utility for pi, right? In the direct utility estimation, we only learn the utility for a particular policy, but in this case, we can learn the full utility function for the optimal policy, assuming that our estimate for R and our estimate for the transition probability are accurate. So of course, any error we introduce by noisy estimates of these two functions will translate to error in the utility function and therefore to the policy. But the good news is if we get enough data, we're going to be able to learn the true optimal policy. So that's adaptive dynamic programming. And the last form of passive reinforcement learning we're going to talk about is, like as I mentioned before, my favorite of the three, which is temporal difference learning. So in temporal difference learning, we make changes to our estimate of the utility for every single action that we observe. So what we're going to do is we're going to observe an action and then a transition and a reward. And from that episode, we update our utility function. And the way we do that is through a really clever derivation. So let's look at the Bellman equation. So this is the Bellman equation on the screen, or at least the form of the Bellman equation for a fixed policy. So the term on the right, this term highlighted in green, is the expected value of the utility that we get in the next state, right? So because there's a probability distribution over which state we end up in, we're going to sum over a weighted sum of the utilities of all the possible future states weighted by their probability. So we can write this down using more statistics style notation with this, expectation term. So now this term highlighted in green is the same thing as the one upstairs, and what it's saying is that it's going to be the utility of state S is going to be the score of state S, the reward value of state S, plus this discounted expected utility of S prime under the distribution of where we're going to end up in of S prime. And if you work through the definitions of expectations, or if you understand how this works, you can see that we can, because the reward of S, the R of S, that is a constant with respect to this S prime variable, right? It doesn't matter what the reward is for our current state if we're taking the expectation over the next state. We can sort of just wrap that all up into one single expectation. So we could write it this way. And with these few manipulations, we can now see that the utility is the expectation of the reward of the current state plus the discounted future utility of the next state. So the intuition is then, in temporal difference learning, we're watching this agent walk around the state space, and it makes a move and transitions from state S to S prime. And when we see it go from S to S prime, we can think of that as a sample from the same distribution that this expectation is describing. So that leads to this temporal difference learning update equation. So this is the temporal difference learning equation on the bottom. And what it does is it sets the current estimate or the new estimate of the utility of the current state to the current estimate plus this alpha times a bunch of stuff term. And this bunch of stuff it easily sort of breaks apart into two pieces. So the first piece is the reward of the current state plus the discounted utility of the next state minus the current estimate of the utility of the current state. So this is the observed utility, and this is the current estimate of utility. And then the alpha parameter is just a learning rate parameter. So what that basically means is the higher alpha is, the faster you're going to adjust your utility score, and the lower alpha is the more sort of conservative you're going to be about trusting your previous estimate of the utility. So this is a really easy update to implement, and it takes a little bit of time to think about what it's really doing. But the idea, just in terms of implementation, is that each time we transition from a state S to S prime, we just run this update, right? We plug in S prime in the green, and we plug in S everywhere else. And the intuition is that the difference inside the alpha, inside the term being multiplied by alpha, is how much we under or overestimate the utility. The term in green is, a way of observing what we think our utility should have been, and then the term in yellow is our current estimate of what the utility is. And if they disagree, then we either raise or lower our utility accordingly. You can also move some of the terms around in this equation to get it so that this essentially forms something like a weighted average of all the utility estimates that we've seen so far. So the benefit here is that temporal difference learning, or TD learning, is really easy to implement, but it does converge slower than adaptive dynamic programming, and it also suffers from the same downside as direct utility estimation, where it only learns the utility of the current policy. So it's not totally obvious how you use this utility function to figure out what a better policy would be. You could imagine using this estimated utility to choose your best action, and then you would hope that then you could continue collecting data and improving your estimate of the utility function, but a strategy like that leaves a lot to analyze before we really understand whether that will actually work. And I actually don't know off the top of my head if it would work or not. But the really great thing about TD learning is that it leads to the famous Q-learning algorithm, which is an active reinforcement learning algorithm that we'll talk about in the next video. So that's what I wanted to go over in terms of passive reinforcement learning. So the takeaway point is that in passive reinforcement learning, we are going to observe a log of behavior, a log of an agent wandering around in an environment, and from that log we want to learn something about the environment. And in direct utility estimation, we just directly try to estimate the utility of the policy that the agent is running, and in adaptive dynamic programming, we try to learn the true optimal utility function for the whole state space by trying to estimate the transition probabilities and the reward values. And then in temporal difference learning, we also try to learn the utility of the current policy, but we do it in a much simpler way and in a way that takes advantage of the structure of Markov decision processes, right? Something that direct utility estimation doesn't do. So try to think about how all this stuff works, and then maybe as a preview, think about how this could be modified in a situation where the agent or the learning algorithm actually has some freedom to decide what the agent should try to do next, right? So rather than just observing a log of behavior, it's observing things as they happen, and it can tell the agent to try certain actions. And then we'll talk about the algorithms that result from that extra freedom in the next video.